Okay, example 6, once again we have a definite integral, and 0 to 4 is the interval. We're evaluating x over the square root of 1 plus 2x dx. And the first thing I want to do is, anytime I see a rational structure, I want to rewrite it so it's got, first of all, radicals as fractional powers, and a negative power instead of a number, a thing on the bottom. I prefer that look. So I'm going to go 0 to 4 of x times 1 plus 2x to the negative half power dx. I just prefer that structure, a negative power instead of a fraction look, because as far as our integration skills are, that's what we know how to integrate. We know how to integrate things to powers, we know how to integrate sine, or like trigonometric stuff, right? So rational structures is something we don't necessarily have an integration technique for, so we have something for a power structure. And in general, if you're looking at one of these things and you see a power structure, something raised to a power, that's probably going to be the argument type. It's going to be a function that's a power. And the argument is going to be whatever the base of that power is. So if I start off there saying that u is equal to 1 plus 2x. And it's a power function, so the argument of that power, which is 1 plus 2x, the base of that power, is going to be u. Bless you. And if I go on, once I've established what u is, to differentiate this and get the differential, I'm going to get du is equal to 2 dx. Which obviously 2 is missing, right? So if I were just to do this and put a 2 here and a 1/2 here, all right? Because again, 2 dx, I need that to be there. So there's du, 2 dx. So the board is turned off. Hang on a second. There it goes. All right. So 2 dx is du. So right there is du. Right here is u to the negative half power. All right. What's the problem? If I change this to u, well, let's just do this. We'll see what the problem is. 1/2, and we'll keep that blank for now. 1 plus 2x negative 1/2 becomes u to the negative half power, right? And 2 dx is du, right? What else goes in there? So this right here is that, and this right here is that.
X.
That x. All right. Still have an x. We have this nasty little x there that's hanging out that's not going away. All right, and that happens sometimes. That you get all this other stuff working for you, but then you have this extra piece in there that is getting in the way, and you cannot integrate that. You can't integrate x and u together with respect to u. All right. It started off as an x problem, so x is important. We're changing x's to u's, making u important, but now x isn't important anymore, so x has to go away. So how you handle this situation is very simple, usually. And the way it is this. Here's the relationship between u and x right here. If I solve this for x, I'm going to get u minus 1 equals 2x divided by 2, right? So x equals u minus 1 over 2. Based on our initial statement that u is equal to 1 plus 2x, we have the ability to solve that for x to get what u or what x equals in terms of u. That means that this expression here can transform that expression there. All right? So if I do that, I'm going to get 1/2. I've got u to the negative 1/2, right? It's being multiplied by x, which I'm replacing with u minus 1 over 2. du. And I can already see on your faces, it looks like we're making this a lot messier than it was, right? And it's like, supposed to make this easier and all that, but we'll worry about that in a minute. Okay. Before I go any further, we started off 0 to 4 here, right? I kind of left it off here, but now this is about x and u. Now it's just all about u, right? So if I go up here, and we know that x equals 0 and x equals 4 is our initial interval, u is equal to 1 plus 2x. 1 plus 2 times 0 is equal to 1, so 0 changes to 1. And 4, 1 plus 2 times 4 is going to be 1 plus 8, which is 9, so 4 changes to 9. So there's our new interval. That has the same answer as the original problem. And again, it doesn't look any prettier. We've got a negative half power, we got fractions, just a big mess. So let's clean this up a little bit and see if we can make this into something a little bit more manageable. Our board is turned off here. Seriously? All right. So, first off, this is over 2, right, which is times a half. So I could just easily pull that half out of here, right? We all see that okay? So if I pull that half out to go with the half that's already there, that makes a fourth. And then if we take a look, and again, that's what happened there. Then if you take a look at this, we have a single object times a binomial, so we do a distributive property. If I do u to the negative half times u, I'm going to get u to the positive half. U to the negative half times negative 1 makes negative u to the negative half du. When I was here to put x inside of this would be very challenging because this is a negative half power. But here it's just something to the first power being multiplied by something else. So then this distributive property is very simple. And now if you take a look at what we have here, this is just a basic power structure. U to a power minus u to a power du. The only power that's illegal right now is the negative first power because we haven't learned that yet. It's possible to do it, we just haven't learned it yet. Alright, so as long as negative first power doesn't show up, it's workable at this point. So if I just do the antiderivative as a power rule, the derivative, our antiderivative of u to the half is u to the 3 halves divided by 3 halves, better known as times 2/3. And the antiderivative of u to the negative 1/2 is u to the positive 1/2 divided by 1/2, which is times 2. And it's minus that, and we're going from 1 to 9. Right. Again, plus c is not necessary because we have a definite integral. The c's will cancel anyway, so just leave it out. Again, each time raise the power divide, which is multiplying by the reciprocal. So reciprocal of 3 halves, 2/3, reciprocal of 1/2, 2/1. So now if I substitute 9 in first, let's scroll this down a little bit. So I got my 1/4. Alright, so if I put 9 in, the square root of 9 is 3, to the third power is 27, times 2 is 54. The square root of 9 is 3, to the first power is 3, times 2 is 6. If I put 1 in, 1 to the 3 halves is 1, times 2/3 is 2/3. And the square root of 1 is 1, times 2 is 2. (54 equals 18. So I get 1/4 times 12, right? And 2/3 minus 2 is negative 4/3, minus makes plus 4/3. (12 plus 4/3 is going to be 40/3. And 1/4 of 40/3 is 10/3. Everything from here down was just evaluation, not a big deal. But the thing I wanted to get across to you is that there's going to be maybe 3 or 4 homework problems towards the end of the assignment. They're going to have this specific thing happen where everything got fixed, but then you still have an x hanging around. If it was x squared, I'd have to square this to put x squared. So if it was x to the third, I have to cube that to get x cubed. But there's going to be some power of x sticking around that's going to be in the way. So you need to use this relationship to get what x equals, and then that allows you to change it out. All right? And then you construct something all about u and create one of these nice power structures that you know how to integrate. All right? And from that point, it just works pretty nicely. And again, with both those problems, definite integrals, once you change it to a completely u integral, change the interval from x to u, this number becomes this number, that number becomes that number based on this substitution choice you made.